Hello there, calculus students. Dr. Shiragi here. We're on the very last section of chapter 4. We're actually beginning to transition into what the last chapter of the class was going to be, which is integrals. This section is called antiderivatives, so make sure you get yourself a copy of the antiderivatives handout that I put together. Antiderivatives are kind of what they sound like. They're sort of the opposite of taking a derivative. Your book uses a nice example of why this is important. You might remember we had all those problems that were about acceleration, velocity, and position, where we had, like, if you had a function that described the position of something at time t, well, then the derivative of that was equal to the velocity. And for that matter, if you had the velocity of the object, the derivative of the velocity was the acceleration of the object. I know some students weren't nuts about that at that time, but see how we were doing this here? But realistically, we could, all the problems there work the same sort of way, where we were given the position function, and then we use that to find things like velocity or acceleration by either taking the derivative or the second derivative. But realistically, we could do it the other way around, right? A perfectly good question would be, if I gave you the acceleration of the object, could you find its velocity? Well, that would be an antiderivative. Or, given the velocity, could you tell me the position of the object? That also is an antiderivative, and that's actually a perfectly useful thing to be working on. Oh, excuse me, I dropped my cloth here. So we need to be able to find this idea of what an antiderivative is going to be. And again, we're going to be really good at this by the next chapter. But for right now, we're kind of just nibbling at it as part of the ending of this chapter about applications of derivatives or whatever. So the book kind of has this definition of antiderivative, which I'm not sure is the most helpful thing, but it probably has to be said at some point, where you say that big F is the antiderivative, I'll just say tick, tick, of little f if the derivative of big F of x equals little f of x. Okay, I'm not sure that's the most, like, that illuminates to me what it's going to be so much as like an example does. This is the example I have there on page 1. If you have some function f of x equals 2x, what is its antiderivative? In other words, what function has this as its derivative? Well, we've done derivatives of things that involve powers enough times to know that the derivative of x squared will be 2x. So this is an antiderivative of this. So here's our answer. The derivative of this is this, so the antiderivative of this is this. Okay, and I should say not say the antiderivative, I should say an antiderivative of it. Because actually, every function out there has an infinite number of antiderivatives. I mean, sure, the derivative of this is this, but wouldn't it work just as well if I had said that my function was 2x plus 3? Wouldn't the derivative of this be 2x? Sure it would. What about if I had said this function was x squared minus pi? Wouldn't the derivative of this be 2x? Sure it would. In fact, anything of the form f of x equals x squared plus some constant c would have been fine. Whether that was positive or negative, a big number or a small number, they all would have worked. So actually, there's always an infinite number of antiderivatives to any given function, and we indicate that by saying plus c, where we could just be adding any arbitrary number at the end. And that's what I have there, cut and paste from your book at the top of page 2 there. That's what they're calling the general form of the antiderivative. So, when we do an antiderivative, and we'll do lots of examples here, they'll always have that plus c on the end, because they will have, we could add any constant and it would still work. And in fact, I did 4 little examples here from example 4.50, and they're pretty straightforward here. Like on the first one, if f of x was equal to 3x squared, what is its antiderivative? Well, we've done enough examples of working with derivatives that involve the power rule in the past to know that it's going to be x cubed plus c, because the derivative of this will be equal to this original function right here, right? The derivative of x cubed is 3x squared. Derivative of any constant c is just 0. All right. The second one that I put on there is a little less obvious. I mean, the derivative of 1 over x, I'm sorry, what function has its derivative 1 over x? Well, you might be tempted to say the natural log of x. I mean, we certainly are close here, right? The derivative of the natural log is equal to 1 over x. I'll leave it to you to read the little description in the book as to why it actually has to be the absolute value of x. You might remember the negative values are out of the domain otherwise. Okay, that's not some huge deal. Oh, hey, plus c. Because the derivative of this will be this. That makes big F the antiderivative of the original function there. The third one, it just shows, for example, that this could work for trig functions. If f of x is the cosine of x, what function has that as its derivative? The derivative of blank is cosine. Well, that's actually sine. The derivative of sine of x plus c, because it could be sine of x plus 1,000,000, sine of x minus 1, whatever, it doesn't matter. Its derivative will be equal to this original function. Big F of x is the antiderivative of little f of x. Just to show it also works for exponentials. F of x equals x e to the x. What function has e to the x as its derivative? Well, that's actually kind of cool. Remember, e to the x is its own derivative, so it's e to the x plus c. Any such function here, its derivative would be this thing. The most important thing I would say about these things is just always make sure you check your work. You know, make sure, does the derivative of this equal to this? Does the derivative of this equals to this? And if you do that and you always check your work, they're going to be fine. Alright? We usually quickly transition out of this idea of antiderivatives and start talking about this as an indefinite integral. That's a good term to know. An indefinite integral. Indefinite integrals and antiderivatives are kind of the same sort of thing. We would say that the indefinite integral of f of x is going to be equal to big F of x plus c. It's equal to its antiderivative plus c. Alright, what makes this an indefinite integral? See how we've got two symbols here? We've got this sort of curly s thing here, and we've got a dx. Think of those as like the beginning and the ending of like a, you know, like when you use parentheses or something like that. And they're operating on the thing in between them, in this case f of x. Okay, so you always have to write it that way, where like, you know, it'd be the indefinite integral of x cubed dx. What makes it an indefinite integral is there's no little numbers here. You're going to see some ones later that have like 1 to 3 on the ends here. Those will be definite integrals. Right now we're doing indefinite integrals. They don't have little numbers there. They're going to be useful for other purposes. So this is just the definition of what we mean by an indefinite integral. So like, for example, the indefinite integral of 2x dx will be whatever this thing is here, find its antiderivative. We already have done that. It's x squared plus c. So the indefinite integral of 2x dx is x squared plus c. Actually, much like was the case with derivatives, where we quickly learn some rules that make things a lot easier, probably the best and most important rule in indefinite integrals is its power rule. If you have any kind of integral of like x to the nth power, okay, so see how we wrote this here, indefinite integral of x to the n. Hey, by the way, this thing on the inside here is called the integrand. It's called an integrand. The indefinite integral of x to the n is going to be x to the n plus 1 divided by n plus 1. And then plus c on the end here, because that can be any constant. So it's real straightforward. I mean, the indefinite integral of x to the 7th dx is equal to x to the 8th over 8 plus c. And you can always check that. Take the derivative of this and make sure. In fact, that's what we do there in some problems toward the end where we call verifying it. Take the derivative of this and make sure it's equal to this integrand. Now, on the third page, I cut and paste. They're probably too small to really see very well there, but they kind of remind you to go back to the book. I pasted a bunch of integral rules for indefinite integrals. That's mostly that second column of the book, of that sheet right there. But for example, that shows that the indefinite integral of the cosine of x dx will always be equal to the sine of x plus c. Or whatever. There's a bazillion of the, well, a bazillion, like 10 of those right there. That'll be useful for you in your homework here. You know, you don't have to memorize these or whatever. You would have a sheet with these on them for the next test provided to you. Okay. So you can have that kind of set of rules right there. Another important rule is on the 4th page there, that is about some of the properties. For example, the way they wrote it on there was that if you have the integral of the sum of two functions, that's going to be equal to the integral of the first one plus the integral of the second one. In other words, if I have like the integral of x squared plus cosine x dx, that would be the integral of this first one plus the integral of the second one, both of which are ones we know. That would be x cubed over 3 plus sine x plus c. Alright, so the integral of a sum is just the integral of the pieces of the sum. That's pretty straightforward. For that matter, the other part of that rule there, for constant multiples, if you have like the integral of some constant times a function, you could take that constant out and just do the integral of the function on the inside. So like for example, if you have the integral of 8x squared dx, that's going to be 8 times the integral of x squared dx, which will be 8 times x cubed over 3 plus c. Alright. There's 2 more examples there in the handout to work through. One of them, the one that's in the middle of the page, is just a verification, where you just take the result on the right-hand side of the equation and take its derivative and make sure you get that original integrand back. So like if I took the derivative of 8/3 x cubed, will I get 8x squared back? 8 cubed times 3x squared, these cancel out, I get 8x squared. See, I got the original integrand back. That's called verifying an integral, and that's what we do in that middle one right there. Or sometimes the problem is going to ask us to actually evaluate an integral. Oh man, we're going to be doing so much more of this stuff in Chapter 5. We really do just sort of get our feet a little bit wet on this right here at the beginning, or at the end of the previous chapter, I guess I would say. It's asking us to evaluate 5x cubed minus 7x squared plus 3x plus 4 dx. I really like it too when you kind of put these in parentheses inside here, just to make sure it's clear. I mean, here's the beginning, here's the integrand, let's use that word again here, integrand. And here's the dx, that means we're done with it. That's the ending and closing. They actually have meanings, we'll get there as to what that all means, but for right now I think that's a helpful thing to write it out like that. Alright. Well, remember, like the sum of, if you're integrating a sum, it's the same as integrating the pieces of this. So that would be integral of 5x cubed dx minus the integral of 7x squared dx plus the integral of 3x dx plus the integral of 4 dx. And actually, each of these, notice we have a constant in front of the function. So we can just pull those out. 5x cubed dx minus 7 times the indefinite integral of x squared dx plus 3 times the indefinite integral of x dx plus 4 times the indefinite integral of nothing dx. That's the same thing as saying like x to the 0th power. Alright, well these are all just power rules then. 5 times x to the 4th over 4 minus 7 times x to the 3rd over 3 plus 3 times x squared over 2 plus 4 times x over 1 plus c. And that's our answer. Neat! I don't know for sure why textbooks always include antiderivatives at the end of this chapter about applications of derivatives. The truth of the matter is this would probably fit better in the next chapter, but maybe there is some teaching reason that I've never quite figured out. Anyway, I think they're pretty cool little things. The assignment for this is pretty small, and this time there's no exit ticket. So I think we're going to have this under control. Go ahead and get to work on that assignment, and please let me know if you have any questions. And, you know, we're going to have a test pretty soon. We're going to have some reviews, and then we'll have some kind of test. All right. You guys take care of yourselves, and let me know if you have any questions.